morning friends. After the discussion of mode of oscillation or the mode of harmonic in a string. Now, what are the mode of oscillation or the mode of harmonic produced in a pipe? Pipe are two kinds, closed pipe and open pipe. Right? First, we are going to discuss about that, the stationary wave in a pipe. Now, in a column inside a pipe, the stationary waves are produced due to reflection of wave of definite frequency. Right? In a column, inside pipe, the stationary wave are produced due to reflection of wave of definite frequency. Definite frequency. So how the waves are generated in a column of a pipe? So here one wave is going inside, that is the reflect from the surface of the water, or in open pipe that is the return wave. So both waves are supposed in a medium inside a pipe. Therefore the stationary waves are produced in a pipe. Right? Pipes are two types. Pipes are two types. One is open pipe, the pipe which are open from both ends. Open from both ends is known as open pipe. Example is fluid. Example is fluid. Now second is closed pipe. The pipe which open from one end and closed at the end. Is known as closed pipe. What is the example of a closed pipe? Water is partially filled in a glass tube. So that is the example of closed pipe. Example is partially filled water in a glass tube. For both open and closed pipe, we are obtaining the stationary wave or the mode of stationary wave in open and closed pipe. Again, what is the stationary wave, or discuss the stationary wave in pipe and explain the types of pipe. In a column inside pipe, the stationary waves are produced due to reflection of wave of definite frequency. Now, the pipes are two types. One is the open pipe and second is the closed pipe. What is the open pipe? The pipe which are open from the both ends is called the open pipe. Example is fluid. Now, second is the closed pipe. The pipe which open from one end and closed at other end is known as closed pipe. What is the example of a closed pipe? Partially filled water in a glass tube. Right? Now our next question is that explain the stationary wave in a closed pipe and obtain the equation of normal mode for the different mode of oscillation. Explain stationary wave in a closed pipe and obtain different mode of oscillation, or the obtain equation of different mode of oscillation. Sometimes this question is also asked like this way. Explain the stationary wave in closed pipe and prove that only the odd harmonics are obtained in closed pipe. Our question is that explain stationary wave in a closed pipe. And prove that only odd harmonics are possible in closed pipe. So, for the stationary wave, for the discussion of the stationary wave in closed pipe, here we consider a glass tube partially filled with water. Right? The open end is act as a antinode, and the water level for the water end, for the closed end, is act as a node. Because the water end cannot be moved, that is the fix. Therefore, the node is produced at water level, and also at open end, the antinodes is produced. For that purpose, consider a glass tube partially filled with water. Right. Now, the end in contact with water. The end in contact with the water is node, and open end is antinode. Now, at node points, at the node, the pressure is maximum, but the pressure changes is maximum. Therefore, the displacement is at node points. The pressure changes is maximum, but the displacement is minimum. While at the open end, that means at antinode points, the pressure changes is minimum and displacement is the maximum. Now at node, pressure changes is maximum, but displacement is minimum. Approximate zero. And at antinodes, the pressure changes is minimum. Pressure changes changes is minimum, but displacement is maximum at empty nodes. Because already the definition of the empty node we know that the point at which the amplitude is maximum is known as the empty node, and the point at which the displacement is zero or the minimum, that is as a node. Clear this? Okay. Now, here we consider a glass tube partially filled with water. Right? Therefore, what's happened like to this way? There is the glass tube partially filled with the water. So up to this, there is the filled with the water. So this end is act as a node points, while the open point is act as a empty nodes. So here the pressure changes is maximum, but the displacement of this point is minimum. While here the pressure changes is minimum, but the displacement of this point is maximum. Therefore, it is act as a empty node, and that is act as a node points. Clear this? Okay. As we consider there is the x is equal to 0, and this end is x is equal to L. So in short, at x is equal to L distance, the displacement is maximum. That means the amplitude is maximum. In a stationary wave, the equation of the stationary wave is y is equal to 2a sin kx cos omega. This term represents the amplitude of a stationary wave. So this amplitude is maximum at open point and minimum at this point, closed point. Therefore, at open point, the amplitude becomes the maximum if and only if sin kl is the maximum. Maximum value, that means the 1. Clear this thing? We are using this concept. At n, that means the x is equal to n. That means at empty node points, now at empty nodes, x is equal to L. For x is equal to L, amplitude is maximum. Amplitude is maximum. Therefore, the sin kx is equal to 1. Therefore, taking the x is equal to L, therefore kl is equal to n plus 1 by 2 into pi. N plus 1 by 2 into pi. But k is equal to 2 pi upon lambda. Therefore, 2 pi upon lambda into L is equal to n plus 1 by 2 into pi. Pi cancel. Therefore, what is the equation of L? What is the equation of L? Therefore, L is equal to n plus 1 by 2. These 2 upon lambda taken on right hand side, it becomes the lambda by 2. This equation is also written as 2 is the LCM, 2n plus 1 by 2. Therefore, 2n plus 1 into lambda by 4. 2n plus 1 into lambda by 4. There is an equation of length of a column in a closed pipe. And possible wavelength lambda is equal to, from this equation, 2L upon n plus 1 by 2, or they can be written as L upon 2n plus 1. That's the equation number 2. That is the equation of wavelength of stationary wave possible in a open pipe. So a closed pipe. Right. And frequency of oscillation. and frequency f is equal to, already we know that in string the n v upon 2n, here instead of the n plus 1 by 2 or the 2n plus 1. Therefore n plus 1 by 2 v upon 2n, v upon 2n, or that can be also written as 2n plus 1 v upon 4. This is the equation of the frequency. Again, at NT nodes, the amplitude is maximum. Therefore, in equation of the stationary wave, 2a sin kx must be maximum. So, amplitude is depends on the sine function. Therefore, the value of the sine function must be 1. Therefore, sin kx is equal to 1. Now, NT node is at point x is equal to l. Therefore, we take, instead of the x, we take the l. Therefore, KL is equal to maximum value of sine is n plus 1 by 2 into pi. Right? But the k is equal to 2 pi upon lambda, that is the wave vector. Substitute here, 2 pi upon lambda into L is equal to n plus 1 by 2 into pi. Pi cancel, and equation of the length L, L is equal to n plus 1 by 2, and that is lambda by 2. We can also write this equation in that form, 2n plus 1 into lambda by 4. And possible wavelength, lambda is equal to, here 2l upon n plus 1 by 2 or 4l upon 2n plus 1. And frequency, f is equal to n plus 1 by 2 into v upon 2n is equal to 2n plus 1 into v upon 2n. Right? Here the value of n, where n is equal to 0, 1, 2 and so on. Yes, we take the different value of n in these three equations. So we obtain the different mode of oscillation or the different harmony in case of a closed pipe. Clear this? So again we repeat the stationary waves for this question is important, and here the equations are important for the numerical and MCQ type question. Explain the stationary wave in closed pipe and obtain the equation of the different mode of oscillation. For this question we also ask, explain the stationary wave in closed pipe and prove that only the odd harmonics are possible in closed pipe. So consider a glass tube partially filled with water is act as a closed pipe. Right? The end in contact with water is node and open end is antinode. At node points, the pressure changes is maximum and displacement is minimum. While at the antinodes is at open end, here the pressure changes is minimum but displacement is maximum. Therefore, at antinodes is lying at x is equal to L distance from the water surface. Therefore, amplitude is maximum. For maximum amplitude, sin kx must be 1. That means the sin kl is equal to 1. Therefore, kl is equal to n plus 1 by 2 into pi. Therefore, but k is equal to 2 pi upon lambda. Substitute here, 2 pi upon lambda into L is equal to n plus 1 by 2 into pi. Pi cancel. Therefore, we obtain the equation of L. L is equal to n plus 1 by 2. This 2 upon lambda taken this side, lambda by 2. So that is here we take the 2 is LCM. Therefore, 2n plus 1 into lambda by 4. That is our equation of length. And possible wavelength is lambda is equal to 2l upon n plus 1 by 2 or 4l upon 2n plus 1. And frequency f is equal to n plus 1 by 2 into v upon 2l is equal to 2n plus 1 into v upon 4. Here the value of n is either 0, 1, 2 and so on. By taking the different value of n, we obtain the different mode of oscillation in a closed pipe. Clear? Okay, we are going to obtain this thing. Okay, now taking the different value of n in our equation of length, wavelength, and also the frequency. Right? Now taking n is equal to 0, the frequency of oscillation is F1 is equal to, our equation is 12 upon 2n. So 2n plus 1 into V upon 12. Our equation of the Fn is F is equal to 2n plus 1 into V upon 12. As we take n is equal to 0, therefore F1 we obtain V upon 4n. Is our F1, that is the first harmony, first or fundamental harmony. And wavelength λ1 is equal to 4n. And length L is equal to λ1 by 4. Therefore, figure becomes like this manner. There is the glass tube partially filled with a water. So to fill up to this. So that is why x is equal to 0, and this point in x is equal to L. So in L length, λ by 4, that means the fourth part of one wavelength is produced. So here there is the node points, and open end is act as a in P nodes. Therefore, there is format like this manner. This mode of oscillation takes place in A column this way. There is the λ by 4. Right? This F1 is known as the first or fundamental harmony. Now, for n is equal to 1, there is the first or fundamental harmony. First or fundamental harmonic for the mode of oscillation. Now, if taking n is equal to 1, therefore what's happened? So f is equal to, our equation is this 1. So 2 plus 1, 3v upon 12, 3v upon 4n. But the v upon 12 is our f1. Therefore, 3f1. So directly third harmonic is obtained. Third harmonic is obtained instead of the second harmonic, because the fundamental frequency is 3 times. Right? Therefore, there is the f3. And λ3 is what? Equation of the λ is 4L upon 2n plus 1. 2n plus 1. Therefore, 1 2 plus 1, 4 by 3, 4L, 4L by 3, 4L by 3. And length L is equal to 3 lambda by 4, 3 lambda by 4, ROT. F3 is called third harmonic or first overdone. First overdone. Therefore, the figure is like this manner. L length of a tube partially filled with the water. There is the x is equal to 0. This point in x is equal to. So here in L length, Hubble's wavelength is formed 3 by 4. 3 by 4. It means the 3 part of one length, 1 by 4, 1 by 4. Out of the 4 part, 3 part of wavelength are produced. So in short, here we can take like this manner. So here 3 part, 1, 2, and 3. 1, 2, and 3. Therefore, our wave is produced like this manner. So there is the one part, there is the second, and there is the third part. So here this point is antinodus, this point is also antinodus, and this point is our node points. So there is the second harmonic or first overdone. Second harmonic or first overdone. Sorry, third harmonic. First overdone. Now taking n is equal to 2. N is equal to 2. We obtain the F3 is equal to 2 into 2, 4 plus 1, pi V upon 4L. Pi V upon 4L. But the V upon 4L is equal to F1, therefore pi times F1. And there is our lambda pi, F5, and wavelength is lambda pi is equal to 4L by pi. And L is length of a column. L is equal to pi lambda by 4. Pi lambda by 4. Here is, therefore, what is the shape of this first fifth harmonic? So F pi is called fifth harmonic or second overdone. Second overdone. So this second overdone is shown in the figure. Here we do the diagram of fifth harmonic. So partially filled with water. This point is act as a node, and upper point is act as a antinode. So here the stationary wave are produced in such a way that the lower point is node and upper point is antinode. And pi part of 1 by 4 lambda are generated in L length. That is the x is equal to 0. That is the x is equal to L. Therefore, like this manner. So waves are generated like this form. So that is known as the fifth harmonic. Fifth harmonic or second order. Second order. Thus, in a closed pipe, only the odd harmonics are possible. Thus, by taking n is equal to, up to 2 we take n is equal to 3, 4 and so on. Right? 7th, 9th and more harmonics are obtained. Thus, in a closed pipe, only odd harmonics are possible. Odd harmonics are possible. The equation of the general equation of frequency and wavelength of nth harmonic for closed pipe is Fn is equal to Fn is equal to n plus 1 by 2 into V upon 12 or 2n plus 1 into V upon 4. And wavelength lambda n lambda n is equal to 2n upon n plus 1 by 2 or 4n upon 2n plus 2n plus 1. So that is the stationary wave produced in closed pipe. Now listen again. Now taking the n is equal to 0, the frequency of oscillation is F1 is equal to V upon 4n. That is known as the first or the fundamental harmonic. Now, in wavelength, lambda 1 is equal to 4L and L is equal to lambda 1 by 4. Therefore, the first harmonic shown in, or the A column inside a closed pipe oscillate with the first harmonic, the stationary wave produced are shown in the figure. So, that is the first or the fundamental harmonic. Now, taking the n is equal to 1, next value of n is after the 0, 1. We substitute here, therefore directly F3 is obtained. Why we take the F3 not F1? Because that is the second value. But here the frequency obtained is 3 times of the fundamental frequency, 3 times F1. Therefore that is the frequency of directly third harmonic, even harmonic is absent. Therefore 3 F1. And lambda 3 is equal to 4n by 3 and required length of a column is 3 lambda by 4. So in L column length, the 3 by 4 lambda waves, stationary waves are produced. And F3 is called the third harmonic, that is also known as the first overall. So the third harmonic is shown in the figure. 3 parts of 1/4 lambda are possible in Ln. 1 part, second, and third. So nodes and antinodes points are this. Right. Now taking the n is equal to 2, what's happened? Therefore the 5 times V upon 12 is F1, therefore 5 times of fundamental frequency, therefore fifth harmonic is directly obtained instead of the fourth harmonic. And wavelength of this harmonic lambda phi is equal to 12 upon 5 and length L is equal to pi lambda by 4. So F phi is called the fifth harmonic or the second order. The figure of the fifth harmonic is shown in the figure. Now listen. Thus, by taking the different value of n, 3, 4, and so on, the 7, 9, and more harmonics are obtained. Only the odd harmonics are obtained. Thus, in a closed pipe, closed pipe, only odd harmonics are possible. The general equation of the frequency and wavelength of nth harmonic for closed pipe is Fn is equal to n plus 1 by 2 into V upon 2n or 2n plus 1 V upon 4n. And equation of the wavelength lambda n is equal to 2n upon n plus 1 by 2 is equal to 12 upon 2n plus 1. Clear this? So these are the stationary waves and only the odd harmonics are possible in a closed pipe. Clear this? Okay. After that, we are going to discuss about the harmonic or the stationary wave in open pipe.